Hi there, class. Welcome back to another lecture. And in today's lecture, we're going to start the chemical equilibria lecture. So this is going to be chapter 13 in your OpenStax book. And we are going to cover the first two sections, 13.1 and 13.2 in this lecture. And the main reason for that is that 13.1 is such a small section, just giving an overview of what equilibrium is, that I figured instead of making one 5-minute video and then another that's 20, we'll just combine them together and move forward from there. So let's take a look at chemical equilibria. So chemical equilibrium is really defined by two different parts of a combination that comes together to make this state. So the first part is that the forward and the reverse rates of a reaction are going to be equal when a given reaction is defined as being in chemical equilibrium. And then the other half of that is that the concentration of reactants and products will no longer change with respect to time. So obviously as you start a reaction, you're going to have all reactants and no products. And then as you continue and the reaction moves forward, you will start to produce products, you will start to diminish some of your reactants. And then when we're talking about something that is in equilibrium, there's a back and forth. So equilibrium is always going to be dealing with a reversible process. Now keep in mind, we've stated in the spontaneity lecture that all of these processes are reversible to some extent. You just have to manipulate the conditions in the correct way. It's very rare to have a completely irreversible reaction. You should be able to find conditions in which they can become reversible. But it is very important to remember when we're dealing with equilibrium, reversibility has to be accepted because the first key here, having forward and reverse rates that are equal to one another, it cannot be one-sided where all of it is going to the product side or the reactant side. There has to be a balance. Now, I do want to mention, while this chapter will primarily focus on chemical equilibrium, there is such a thing as physical equilibrium, which is where we're talking about states of matter and two states of matter that are in equilibrium with one another. So you could have a liquid and a gas, and the liquid, based on vapor pressure, is slowly going into the gas phase, and there's a certain amount in the gas phase that is condensing back into the liquid phase or going back into the liquid form. And so you can establish an equilibrium between physical states as well as a chemical process that's going back and forth. Now, the same rules would apply as far as forward and reverse rates when we're talking about the physical process. So let's discuss how we actually start doing some of the math and the setup for these equations. So you can see the generic equation A plus B goes to C plus D. Now, there's little a, b, c, and d, and we've sort of discussed this in our prior lectures for thermodynamics. But these small letters, these lowercase a, b, c, and d, represent the stoichiometric coefficients, and then the large a, b, c, and d are the actual reagents or products themselves, those identities. And specifically, when we start talking about equilibrium, it's going to represent the concentration. Now, one of the things that's important here is you can see the arrow that is linking the A and B to the C and D is a single-headed double arrow. So each, meaning there's two arrows, it's a double arrow, one going in the forward direction, one going in the reverse direction, but they are each single-headed. And this is the way that we represent equilibrium when we're showing it in a chemical reaction. We're talking about the ability to go back and forth at equal rates, and so therefore we should have arrows of approximately equal size that each have one arrowhead looking as it does in the above equation there. So prior to this, most of the time we've been using one-directional double-headed arrows, meaning A plus B, and then we show one arrow going in one direction, and then that yields C plus D. So you're going to see some of this new drawing format when we start getting ready to utilize these equations. All right, so this refers to the reaction being shown in a state of equilibrium compared to the single double-headed arrow, which refers to only one direction of the reversible reaction. So the equilibrium constant, every reaction that can be established at equilibrium, that equilibrium is going to have a constant or a known value that is associated with it. And this can help us in identifying concentrations for reactions. If we know that a given reaction has a certain equilibrium constant, we can then go in, and if we know the concentration of some reactants or products, we might be able to predict the others through math. Right? So we can utilize the equilibrium equation for any given reaction and create what's called a reaction quotient. And you can see this is represented by Q sub C. Q sub C, the reaction quotient, is technically not the equilibrium constant. It is calculated in the same way, but it is just a quotient factor as we move on our way to equilibrium itself. And then when we're at equilibrium, the reaction quotient therefore becomes referred to as the equilibrium constant, and we use K instead of Q. So we'll get to that in a minute. But the reaction quotient is going to be used to determine how the concentrations will affect the equilibrium state. So is it going to be more in a product-driven state or more of a reactant-driven state in terms of concentrations, right? And you can see I have it set up here with the quotient, so QC equals the concentration of C raised to its stoichiometric coefficient times the concentration of D raised to its stoichiometric coefficient, and so on and so forth. So you can see what I've put under here is a generic setup for all of this, where it says where X, large X in brackets, is the concentration. So X could be C, D, A, or B in this case. And then the lowercase x is the stoichiometric coefficient. Again, we should be familiar with this from our thermodynamics material. All right, so at the initial starting point of a reaction, this is important to remember, QC must be equal to 0. And that's because no products have been formed yet, and the numerator of the expression is 0. So if I go back real quick, you can see C and D, or if I go back again, C and D are the products. So it is just like when we did thermodynamics, it was the summation of products minus the summation of reactants. Here it is going to be the quotient of products, and that's going to be divided by the reactants. So C and D, the products at the very beginning, the initial state, as soon as you put the reactants together, has to be 0. So if the numerator of any quotient is 0, by default, that has to become 0 then mathematically. So this makes sense. QC is going to be equal to 0 as no products have been formed, and the numerator for the mathematical expression is 0. Now, this should make sense, okay, because no equilibrium value can be achieved before a reaction actually takes place. So for a forward and a reverse rate to be equal to one another, you have to allow time for those reactions to actually come into existence, so to speak, once you mix the reactants together. At time 0, or at the initiation point of your reaction, it's not going to be possible to have equilibrium. So after the reaction starts and you allow these chemicals to start reacting with one another, okay, the QC value is going to increase because naturally as the reactants do what they're supposed to do, they react, you're going to start forming some products. And we're going to see QC start to climb, and it will increase until we arrive at equilibrium. And when equilibrium is achieved, it's at that point that the value will remain constant. And that's by the very definition of equilibrium that we had on that first page that we were talking about. So here we can take a look at it in a graphical representation. All right? Now it says here, you can see at the top, equilibrium constant QC to KC. So KC is used to represent the equilibrium constant or the equilibrium quotient, and the QC is anything leading up to that KC state. So if you take a look at the graphical representation here, along the x-axis is time, because we need to give some amount of time for a reaction to occur, and then the y-axis is the reaction quotient. And what's happening over time? Well, at time 0, the reaction quotient is 0 because nothing has reacted. And then as that numerator value continues to creep up and increase as we make reactants and as we make products and the concentration of the products start to increase bit by bit, we start climbing up on this scale. Now at a certain point, by the very definition of equilibrium and reversibility, we are going to reach a point where the forward and the backward reactions are equal to one another. And when that happens, there is no longer a change in concentration. And if there's no longer any change in concentration, then the reaction quotient becomes stable or constant, and therefore the reaction quotient is no longer QC, but it becomes KC, a constant which we are establishing. All right, so QC it might be constant at one specific set of concentrations, but it's a moving target until we hit Kc. And then Kc is what levels out here, the equilibrium constant, and that will stay completely at the same value the whole time. So let's talk about evaluating Kc for a moment. When we are evaluating the equilibrium constant, the magnitude of the value can tell us something regarding the reaction. So this is kind of similar to in the thermodynamic lecture when we were talking about if we have a delta H that's negative and a delta S that's positive, then that indicates a Gibbs free energy that should be negative and will proceed spontaneously under all temperatures. Right? So these are general guidelines if you see certain values popping up. Right, so when Kc is a large value, and we're going to define large as being over 1 in this case, the equilibrium state is favoring the product formation over the reactants. So keep in mind what Kc actually is mathematically. Products over reactants. So if the value is greater than 1, the numerator has to be larger than the denominator. Well, the numerator is the products, the denominator is the reactants. So if Kc is over 1, then the equilibrium state is favoring products over reactants. Okay, that doesn't mean that it favors the rate of products more. The rates are equal. It is simply favoring more product over reactants once those rates are established. All right, when Kc is a small value, and we're going to define that as under 1, the equilibrium state is favoring the reactant formation over the products. Now this is the same exact premise, but now we are talking about a larger number in the denominator. So when you have a large denominator and a small numerator, you're talking about a fraction, so it's going to be something under 1. Okay, and there are rare cases where Kc is going to be equal to exactly 1, and we can state that the reaction does not favor either the products or the reactants in that case. The concentrations would not only be constant, but they would be equal to one another. And that's the only case where we would get 1. And that's not going to happen very often, but it's certainly not impossible. All right. Now, when we start breaking down these equations, and we start looking at the different states of matter to determine Kc, it is very important to remember that we will be excluding solids and liquids from any equilibrium concentrations. Okay? Now, the reason behind this is that most of the time, liquids that are going to appear in any type of reaction are either going to be solvents, which means they're not reactants, or when they are produced, they are not actually being utilized in the reaction. Okay, so what happens is they are not a significant contributor to the Kc value overall. And many solids end up being precipitates that come out of reaction. So what is it that we're looking for? We're looking for gases, and we're especially looking for aqueous material. So anytime we see ions or aqueous-based solutions, those are what we are using in order to calculate Kc. But we are going to omit solids and liquids because they do not end up really coming into the Kc calculation and contributing to a significant portion. All right, what is Kp? Because there are multiple ways that we can evaluate the equilibrium constant, and the OpenStax book discusses this. So Kp is really looking at when we have gases, the pressure of the gases. So we're used to talking about Kc, and we haven't even mentioned it up to this point, but what does the C stand for when we have that little subscript? It stands for concentration. So when we're talking about concentration, we are usually referring to molarity, although there are other means of concentration. And anytime you see the aqueous solutions, we'll be talking about concentration. But when we get to a gas, you could use either the concentration of that gas, so you can still do Kc for gases, and we'll see that in a minute when we do examples, but you can also do Kp, and Kp is referring to the pressure, specifically the partial pressures. So you can relate Kc to Kp, and you do that through using the gas constant and temperature, which is known as RT. So if you remember from Chem 111, you had PV equals nRT, which was the ideal gas law, where R is the gas constant, and that gas constant was 0.0821, and the unit was atm liters per mole Kelvin. So that's the same R that's going to come back into play here when we start calculating partial pressures with gases in order to find Kp. Now, we can relate these directly using RT by looking at a factor of RT per the total difference in molar coefficients between products and reactants. And I know that's a mouthful. You might be wondering what that means. So all that it really means is take all of the stoichiometric moles that you find for the products, and then from that, you want to subtract all of the stoichiometric moles that you find for the reactants. So let's say that I find 4 moles of product and 2 moles of reactants. 4 minus 2 is 2. So then you can take Kc times RT to the second power, because it's 2, and that will give you Kp. So we will work out an example so that you can see this and kind of concretely relate it to the actual numbers here. So what I'm going to do at this point is I'm going to go ahead and pull up the whiteboard. We will do one example, and both these examples come directly from your OpenStax book. We will do one example that involves the calculation of a Kc, and then we will do one example where we are given Kc and we need to find the Kp in relation to that. And after that, we'll wrap it up. And of course, as always, our class time will be dedicated to solving a lot of these types of problems. So expect a lot of practice in class outside of the examples here, but these are just primers so that we have an understanding going in what we're doing here. So let me bring up the whiteboard. All right, everyone. So let's take a look at our first example here. And in the first example, what we're going to do is attempt to calculate an equilibrium constant Kc. And this is from a problem in your book. So the example that they give has 2 nitrogen dioxide as a gas, and it is in a state of equilibrium with dinitrogen tetraoxide, also a gas. So this is our balanced equation here. Now it says at equilibrium, which I'm going to abbreviate EQ here, the concentration of the nitrogen dioxide is found to be 0.016 molarity. And then it says that the concentration of the dinitrogen tetraoxide is found to be 0.042 molarity. All right, and then the question that it asks is, let's determine and figure out what Kc is equal to in this case. So what we need to do is set up the equilibrium constant. We can say Kc equals. Now what I'd like to do is write this initially as just its product and reactant form, and then we can add the numbers in and solve for the math. So Kc is going to be equal to products, the N2O4, the concentration of it specifically, over the concentration of reactants. And in this case, it's NO2. And the NO2 needs to be squared because we have this value up here. And when we have the stoichiometric coefficient, if it's greater than 1, we need to raise it to that power in order to get the correct Kc. So what we would then set this equal to, pulling the numbers into this, is we would have 0.042 molarity over 0.016 molarity, and this value would be squared. So the resulting value that's going to come out of this, if you put that into your calculator, would be 1.6 times 10 to the second. And there is no unit because molarity drops out with molarity, and it's 1.6 times 10 to the second. So when we take a look at this, this would be how we solve for an example using Kc with concentrations that are being given. All right. Also keep in mind significant figures are important here. We're being provided 2 significant figures for each of these, so the answer should only have 2 significant figures. All right, now the other question is, let's relate Kp to Kc. So this next question says we have the following: carbon disulfide as a gas plus some hydrogen gas, 4H2 gas. Okay, and this is in equilibrium with methane, which is CH4 gas, plus some H2S gas. Now, it specifically says the Kc is going to be 0.28, and that is at 900 degrees Celsius. And the question is, find the Kp for this setup given what has been provided. So what we want to do is calculate Kp using the Kc value, using RT, and then finding the difference in the molar ratios between reactants and products. So let's first find that molar difference. So we can write it as delta little n equals, and it's the total stoichiometric moles that I find over on the product side. In this case, I have a 2 in front of the H2S, and I have a 1 in front of the methane, so that's going to be 3. And then I would subtract that from the total number that I find over here on the reactant side, which is 4 and an implied 1, so that's 5. So the difference here is going to be -2. So that means that I'm going to have RT raised to the -2 when I finish this. So let's put this together then. What I want to do is take Kc, which they gave as 0.28. So Kp, which is what we're solving for, is going to be equal to, in this case, Kc times RT, and that RT is raised to the -2. So the values that we can put in here, we know what Kc is. Kc is going to be 0.28. And we know what R is. R is going to be 0.0821. I am currently going to leave the units out just for space, but that is the ATM liter per mole Kelvin. Okay, and then the temperature, which I'm going to want in Kelvin because I have to get it to mix with this R unit that uses Kelvin, right, I would need to take 900 and add 273.15 to the Celsius. So 900 plus 273.15 would be 1,173.15, right? And this whole chunk here, the RT, is going to be to the minus 2. And if you take a minute and you plug all that into your scientific calculator, you should get 3.0 times 10 to the negative 5th. And again, only 2 sig figs here, so that has to be observed in the answer. So here's our answer right here. Okay? This would be Kp. And that's how you can relate Kc and Kp to one another. You would simply need to be able to find the delta N, and then you would use that with the coupling of RT and your Kc. So that ties up all of the math that we're going to show in this lesson, because we are starting to close in on half an hour here. So we will certainly practice more in class together. So let's finish up. All right, so up next is going to be what is known as Le Chatelier's principle. And Le Chatelier's principle is going to be a situation where, sort of like the entropy, we are going to be given an example and we have to predict something based on that example. So when we had entropy, we were predicting the sign based on what was going on. Here, what's going to happen is you will either be adding components or taking components away from the equilibrium state. And when the equilibrium state is disturbed, it's going to shift into a direction in order to reestablish equilibrium. And so the question is, which way does it move based on what we do? So if we add more product, what's it going to do? If we take away some reactant, what's it going to do? So on and so forth. So I will see everybody over at the next lecture for Le Chatelier's principle. As always, if you have any questions, you're welcome to leave them in the comments or discuss it with me in class. Other than that, thank you for the attention, and I will see everybody over in the next lecture.